Welcome to this explainer on governance and regulatory issues in green computing. Today, we're unpacking a massive topic. Who exactly sets the rules for green IT? And how does global policy actually shape the very systems that engineers build every single day? Have you ever actually wondered why your company's data center has to hit these hyper-specific energy targets? Or why certain hardware choices are suddenly totally off limits? Well, you're in the right place. We're going to dive right into this fascinating intersection of technology, math, and global law. Because, you see, green computing isn't just about, slopping some solar panels on a data center roof and calling it a day. Far from it. It's a highly structured, incredibly comprehensive discipline. The scope we're dealing with stretches all the way from the foundational math of calculating power right up to super strict, globally enforced compliance standards. It requires a completely holistic view. We have to look way beyond just individual servers to understand how entire technology ecosystems are regulated and managed all over the world. To keep us perfectly on track today, here is our agenda. 1. The Green IT Challenge. 2. Mastering the PUE Math. 3. Global Frameworks and Standards. 4. Local Regulations in Bangladesh. And finally, 5. The Engineer's Daily Obligations. Let's jump right into Section 1. The Green IT Challenge, the scale of the problem. The absolute most crucial point to understand right out of the gate is that IT consumes a massive 2 to 4% of global electricity. Let's just put that into perspective for a second. That energy footprint is literally on par with the emissions of the entire global aviation industry. That is a gigantic slice of the world's total power pie that is purely dedicated to running servers, cooling systems, networks, and, of course, our personal devices. And here is the core of the problem. These technologies are expanding at an exponential rate. With the absolute explosion of massive artificial intelligence models, machine learning, and huge high-performance cloud infrastructures, this growth is vastly outpacing the electrical grid's ability to actually supply clean, renewable energy. Think about it. Left to their own devices, companies that are racing to build out these computational networks are naturally going to prioritize cheap, dirty power just to fuel their rapid growth. This fundamental market imbalance is exactly what builds the undeniable case for external rules and really strict governance. Now, green computing fundamentally operates on two complementary tracks. Track 1 is inward-looking, right? How do we engineer our IT systems to simply use less energy? This is all about writing more efficient code and designing low-power server hardware. Track 2, on the other hand, is outward-looking. How do we actually deploy IT to make the rest of the world more sustainable? This involves using advanced computing to do things like optimize global shipping routes, manage smart energy grids, or even model super complex climate change scenarios. The reality is, both of these tracks are absolutely necessary, and both require rigorous regulatory frameworks if they're going to thrive. Moving on to Section 2, Mastering the PUE Math, Calculating Efficiency. But wait, before any policy can actually be enforced, we need a standard mathematical way to measure this efficiency, right? And that brings us to PUE, which stands for Power Usage Effectiveness. I cannot stress this enough. This is the universal language of green IT regulations. It is the absolute gold standard metric used worldwide by engineers and regulators alike to figure out just how efficient a data center actually is. So, here is the exact formula you need to calculate a facility's power usage effectiveness. It's actually pretty straightforward. You take the total power entering the entire facility, and I mean everything, the massive cooling chillers, the overhead lights, the security systems, absolutely everything, and you divide it by the power actually consumed by the IT equipment alone. Let's run a quick micro example. Let's say your facility draws 100 kilowatts total from the grid, but only 50 kilowatts actually make it to the servers doing the computing. That means the remaining 50 kilowatts are being eaten up purely by cooling and infrastructure overhead. Let's look at the results of that math. A mathematically perfect PUE is 1.0. That means every single watt of power goes strictly to computing, with absolutely zero overhead. However, thanks to the inescapable laws of thermodynamics and the physical requirement to actually cool hot equipment down, we can only ever approach 1.0. We can never truly achieve it. So, by contrasting the industry average of 1.58 against world-class numbers of 1.1 to 1.2, we get a really tangible sense of the efficiency gap. An average of 1.58 means that for every single watt used for actual IT work, another 0.58 watts is completely wasted just keeping the room cool and the lights on. Pushing that decimal down is, without a doubt, an engineer's primary objective. Let's shift gears now to Section 3, Global Frameworks and Standards, The rules of the game. This number right here represents the 195 countries that signed the Paris Agreement on climate change. This is the foundational global consensus that essentially cascades all the way down into the specific daily regulations that IT professionals have to navigate. Because when 195 nations commit to drastically cutting their emissions, it means their national governments have to aggressively regulate heavy energy consumers. And you better believe that puts data centers directly in the regulatory crosshairs. And 2030. That is the strict European Union target year for all new data centers to be completely carbon neutral. This implies that a data center's net carbon emissions must be absolutely zero. Period. And that has to be achieved through highly efficient engineering and purchasing 100% renewable energy. Guys, this is not some distant, vague goal. It is a rapidly approaching, hard deadline that is actively forcing companies worldwide to entirely rethink their IT infrastructure today if they ever want to operate within the European market. And to prove these aren't just polite suggestions, regulators back them up with massive penalties. Take a look at this €35 million maximum GDPR fine. Now, while GDPR is primarily known for data privacy, it's really the modern blueprint for how international regulations are strictly enforced. Environmental fines, efficiency caps, and carbon taxes are increasingly being modeled after this exact framework. The bottom line, when governance standards are violated, the financial repercussions are absolutely devastating to a business. So this brings us to the alphabet soup of governance. Let's break down the exact key frameworks you actually need to know. First up, ISO 14001. ISO stands for the International Organization for Standardization, and this specific framework is the world's most utilized environmental management system standard. It basically acts as proof that a company is systematically minimizing its ecological footprint. Next is Energy Star. You've probably seen this one. It's a government-backed symbol for energy efficiency, and it directly dictates the hardware procurement choices you make. Then we have the GHG protocol, which meticulously tracks greenhouse gases across 3 distinct scopes. Scope 1 is direct emissions, like the exhaust from a backup diesel generator on site. Scope 2 is indirect emissions from the electricity you buy from the grid. And Scope 3? That covers your entire supply chain, right down to the emissions created by manufacturing the actual server you just bought. Next is TCFD, the Task Force on Climate-Related Financial Disclosures, which governs how publicly traded companies transparently report these climate risks to their investors. Then there's the EUED, the European Union's Energy Efficiency Directive. This imposes incredibly strict, mandatory operational reporting rules on data center operators. And finally, WEE, or Waste Electrical and Electronic Equipment. This is a crucial directive that mandates exactly how you handle toxic e-waste. It completely dictates how you recycle or dispose of end-of-life servers and hard drives. Look, if you want to empower yourself and truly master the history and application of these policies, these specific chapters from Velit's Green IT and Lamb's The Greening of IT are pretty much your primary source Bibles. They offer incredibly detailed breakdowns of exactly how these frameworks evolved over time and how you can practically apply them to modern infrastructure. Highly recommend checking them out. All right, Section 4. Local regulations in Bangladesh, SRETA, and beyond. You know, global rules are always adapted by national bodies, so you absolutely must understand the specific local focus wherever you are. For example, in Bangladesh, a critical player is SREDA, which stands for the Sustainable and Renewable Energy Development Authority. SREDA is the nodal government agency working to promote renewable energy and strictly monitor energy efficiency nationwide. Understanding their authority is absolutely essential for any local engineer. You really have to know what kind of energy audits they mandate, what specific efficiency targets they establish for large-scale commercial facilities, and exactly how they coordinate the local power grids with the incredibly intense demands of modern data centers. Because remember, you aren't just building for global standards, you are building for the hard legal requirements of the local jurisdiction. And that brings us to our final section, Section 5, the engineer's daily obligations, practical application. Because knowing the rules is really only half the battle. Organizations must actively build systems to document and absolutely prove their compliance. Honestly, it is not enough to just buy green hardware and hope for the best. No way. You have to generate meticulous, undeniable audit trails. This means installing real-time power monitoring software directly at the server rack level, maintaining really strict hardware procurement logs, and capturing deep cooling system telemetry to definitively prove to a regulator or an auditor that you are actually meeting those stringent ISO 14001 or regional SRETA standards. Ultimately, what all this means is that your daily engineering choices are inextricably linked to legal compliance. The server rack cooling designs you draft, the software microservice architectures you deploy, your long-term capacity planning, it is all directly dictated by these governance frameworks. When you select a server today, you aren't just looking at its processing power anymore. You are actually calculating its impact on your company's Scope 3 emissions and figuring out how its thermal output will dynamically alter your facility's overall PUE math. It changes the whole game. So I'm going to leave you with this practical task to apply what you've learned today. Go analyze a real-world data center. Find its specific PUE. Look at the exact engineering choices the operator is making to try and improve that math. Then ask yourself, armed with this detailed knowledge of global frameworks and efficiency standards, how would you engineer a better, greener solution? Because ultimately, compliance isn't just about avoiding a massive fine. It's about actively re-engineering the future of the internet itself. Thanks so much for joining this explainer, and remember to keep questioning the systems around you.